Kubernetes Controllers, the guardians of your cluster. Introduction. Welcome to your detailed guide on Kubernetes Controllers. Kubernetes is the leading container orchestration platform, enabling developers to deploy, manage, and scale applications with ease. Central to its operation are controllers, the guardians of your cluster. These controllers are the silent workers that ensure your desired cluster state becomes reality, and stays that way. In this audiobook, we'll dive deep into all the key Kubernetes controllers. We'll cover what they do, how they work, and why they're essential. Whether you're a beginner or an experienced user, you'll gain insights to help you better understand and manage your Kubernetes environment. What are controllers in Kubernetes? Imagine you have a blueprint of your perfect house. This is your desired state. Now, imagine a group of skilled builders constantly adjusting the house to ensure it matches that blueprint, even if something breaks or changes. In Kubernetes, controllers are those skilled builders. Controllers continuously watch the state of the cluster through the Kubernetes API. They compare the current state of resources, such as pods, deployments, or nodes, with the desired state defined in your configuration. If there's a mismatch, controllers take action to bring the actual state closer to the desired state. Each controller is specialized for specific tasks, ranging from managing pod replicas to handling storage, scaling, or scheduling jobs. Replica set. Kubernetes replica set is a controller that ensures a specified number of pod replicas are running at any given time. It replaces the older replication controller, offering the same functionality with additional support for set-based label selectors. A replica set monitors its pods and automatically creates or deletes them to maintain the desired state. The replica set's desired state, including the number of replicas and pod template specifications, is defined in a YAML or JSON manifest. It uses label selectors to identify the pods it manages. If a pod fails or is deleted, the replica set will replace it by creating a new pod to maintain the desired count. Replica sets are typically used indirectly through deployments, which manage replica sets and handle updates. While you can create a replica set directly, using deployments is generally recommended for managing application rollouts and rollbacks. A replica set ensures high availability and fault tolerance by redistributing pods across nodes in case of failures. It does not manage updates. If a pod template changes, a new replica set must be created manually, or via a deployment. Replica sets are declarative, meaning they continuously reconcile the desired state with the current state. They work seamlessly with Kubernetes self-healing capabilities, ensuring robust application performance. Stateful set controller. Some applications, like databases or message queues, require stable network identities or persistent storage. Enter the stateful set controller. It manages stateful applications where each pod needs a unique and stable name, persistent storage that stays consistent even if the pod is rescheduled. For example, if you're deploying a database like MongoDB, you might use a stateful set to ensure data consistency and reliable communication between replicas. A stateful set in Kubernetes is a workload API object designed to manage stateful applications. It is similar to a deployment but provides guarantees about the order and uniqueness of pods, making it suitable for use cases where state persistence and stable network identities are critical. Key features of stateful set. Stable pod identifiers. Pods in a stateful set are given unique, stable names like stateful set name ordinal, for example, my app 0, my app 1, and so on. Ordered deployment and scaling. Pods are created and deleted in a defined order, ensuring stability for applications requiring sequence-based operations. Persistent storage. Stateful sets work well with persistent volume claims, PVCs, ensuring each pod has a dedicated, stable volume. Ordered updates. Pods are updated in a controlled manner, one at a time, ensuring continuity for applications sensitive to updates. Pod network identity. Each pod gets a stable DNS name, making it easier for other services to reference it reliably. For example, pod0.myservice.default.svc.cluster.local. Use cases. Databases, for example, MySQL, MongoDB, PostgreSQL. Distributed systems like Kafka or Zookeeper. Stateful applications requiring stable storage or network identities. Daemon set controller. Daemon set ensures that a specific pod runs on every node in the cluster, or a subset of nodes if you define it. Common use cases for daemon sets include running log collection agents like Fluent or Filebeat on all nodes, deploying monitoring tools like Prometheus Node Exporter. Daemon sets are perfect for tasks requiring a cluster-wide presence. A daemon set in Kubernetes ensures that a copy of a specific pod is running on all, or a subset of, nodes in a cluster. It is primarily used to deploy system-level services or utilities that need to run on every node, such as log collectors, monitoring agents, or networking tools. Key features of daemon set. Node-level pod deployment. Ensures that the specified pod runs on all nodes or a subset defined by node selectors. Automatic updates. When new nodes are added to the cluster, the daemon set automatically schedules the pods on those nodes, targeting specific nodes. Supports targeting specific nodes using labels, selectors, or taints/tolerations. Minimal overhead. Used for lightweight pods that provide cluster-wide services. Use cases. System monitoring. Tools like Prometheus Node Exporter or Datadog Agent. Log collection. Applications like Fluent or Filebeat to collect logs from all nodes. Networking services. Services like Calico, Flannel, or other CNI plugins. Custom node-level operations. Running custom scripts or agents on every node. Let's review such use case. Centralized log collection for a web application. There is such scenario. A web application is deployed as a deployment or stateful set. Each pod generates application logs, which are stored in the container's stat and stat streams, default Kubernetes behavior. A daemon set deploys log collectors. For example, Fluent, Filebeat, or Logstash, on every node to aggregate and forward logs to a centralized system like Elasticsearch, Splunk, or cloud logging. The job controller is designed for batch processing or tasks that need to run to completion. For instance, sending a batch of emails, performing a nightly database backup, data migration tasks, batch processing, for example, image processing, ETL tasks. Unlike other controllers, the job controller stops once the task is complete. Cron job controller. Need to schedule a job to run periodically? The cron job controller has you covered. It allows you to define jobs that execute on a specific schedule, similar to Linux cron jobs. For example, you could schedule a data cleanup script to run at midnight every day. Use cases. Automated backups, sending periodic emails or reports, cleaning up temporary files or data, regular monitoring or maintenance tasks. Scaling controllers. Horizontal Pod Autoscaler, HPA. The Horizontal Pod Autoscaler automatically adjusts the number of pod replicas in a deployment, replica set, or stateful set based on metrics like CPU and memory usage. For example, if CPU usage spikes, HPA can add more pods to handle the load. When usage drops, it scales down to save resources. HPA ensures your application is always running efficiently without manual intervention. Vertical Pod Autoscaler, VPA. While HPA focuses on the number of pods, the Vertical Pod Autoscaler adjusts resource requests and limits for individual pods. It ensures that each pod has the right amount of CPU and memory for its workload, optimizing performance. Cluster Autoscaler. The Cluster Autoscaler adjusts the number of nodes in your cluster based on workload demands. If pods can't be scheduled due to insufficient resources, it adds more nodes. When nodes are underutilized, it scales down to save costs. Network and Access Controllers. Ingress Controller. The Ingress Controller manages external HTTP and HTTPS access to your services. It allows you to define routing rules, such as mapping a URL like example.com to a specific service, terminating SSL/TLS for secure communication. Popular implementations include NGINX, Trafic, and HAProxy. Network Policy Controller. This controller enforces network policies, controlling traffic flow between pods. For example, you might define a policy allowing only specific pods to communicate with a database pod. Storage controllers. Persistent volume, PV, and persistent volume claim, PVC, controllers. These controllers manage persistent storage in Kubernetes. A persistent volume represents a storage resource, and a persistent volume claim allows pods to request specific storage needs. The controllers ensure that claims are bound to available volumes and maintain the lifecycle of storage resources. Custom controllers. Sometimes, the built-in controllers aren't enough. Custom controllers allow you to define your own resource types and manage them programmatically. For example, operators. Advanced custom controllers for managing complex applications like databases, message brokers, or monitoring tools. The Kubernetes operator pattern simplifies the management of applications by automating day-to-day operations. Conclusion. Kubernetes controllers are the backbone of the platform, ensuring that your cluster operates smoothly and reliably. They handle everything from maintaining pod replicas to scaling applications, managing storage, and securing network traffic. Understanding controllers is key to mastering Kubernetes. With this knowledge, you're better equipped to design resilient, scalable, and efficient applications. Thank you for listening to this guide on Kubernetes controllers. Happy deploying!